In this video, we're going to talk about something called the least upper bound property, which is a property of real numbers. And this is a very important property of real numbers. And as we'll see, it actually distinguishes the real numbers from the rational numbers. So before getting into that, we should define upper bounds and lower bounds. So here's the definition. If S is a subset of real numbers, then an upper bound for the set S is a number, say A, a real number, such that S is less than, little s is less than or equal to A for every little s in the set S. Okay, and if, so that's the first definition, and the second definition is, so if this is the case, if S has an upper bound, then we say that S is bounded from above. So for example, let's say this is your number line, and if your set S is what's going on with the colors? Oh, there we go. If, let's say your set S, okay, let's say this is 0, say, and let's say that S is this interval from -1 to 2, and it's an open interval, and then there's this point here, which is 3. If that's your set S, then an example of an upper bound, right, would be, so any number that's greater than all the numbers in S, so that's every number that's greater than or equal to 3. Right? So in this case, then the upper bounds are all numbers greater than or equal to 3. Now we're ready for another definition. So we say, we call a real number y a least upper bound of S if two things happen. The first thing is if y is an upper bound. Okay, so in order to be a least upper bound, y needs to be an upper bound in the first place, an upper bound of S. And then the second thing is, as you might expect, it needs to be less than or equal to any other upper bound for S. So if A is any upper bound for S, then y is less than or equal to A. So in this, if you look back at this example, with S being the open interval from -1 to 2, and then including the point 3, the least, so the upper bounds of S are all the numbers greater than or equal to 3. So it includes 3, and it's all the numbers here. The least upper bound is just 3. So 3 is the least upper bound for S. And there are a few notations for this. So one of them is, so the notation for the least upper bound is LUB of S, so for least upper bound, or sup S. Sup stands for the supremum. So in this example, 3 is the sup of S. 3 is the supremum of S. Let's look at some examples. First of all, if you can take S to be just a set of real numbers, right? So for example, if S is R, then S is not bounded from above, because there's no number that's greater than or equal to all real numbers. Right? So there's no upper bound for S. Another example is if S is, say, the interval from 0 to 1, so here's 0 and here's 1, and you take all the numbers from 0 to 1 except you don't include 0 or 1, then this has no, in this case, S has upper bounds, because 1 is an upper bound, and everything greater than 1 is also an upper bound, but S has no, so S has upper bounds, but no least upper bound. It does not have, oh wait, that's incorrect. No least, okay, I should rephrase this. It does have a least upper bound, but the least upper bound is not an element of S. That's what I wanted to say. So let me revise that. And the supremum of S is 1. And now notice that the supremum of S is not an element of S in this example. That's what I wanted to say. We'll actually see that every bounded set of real numbers, it's an axiom that it does have a least upper bound. Okay. Now, is it possible for there to be two least upper bounds? The answer is no. So let's make this a remark. Two least upper bounds of a set must be equal. Okay, why is that true? So suppose that there are two least upper bounds of the set S. So suppose y and y prime are least upper bounds of a set S. Well, we know that y and y, so we know that y is an upper bound of S, right? And since y prime is a least upper bound, y prime must be less than or equal to any upper bound for S. That's by property number 2. So y prime is less than or equal to y. But the reverse statement is also true, because y prime is an upper bound for S, and y is an upper bound, and y is the least upper bound, so therefore y must be less than or equal to y prime. Now, okay, so it might be better if I just wrote out more, but that's kind of a lot to write. So I'm just going to say it's because y prime is less than or equal to y, and y is less than or equal to y prime, so you want to think about why that's true, and hence y is equal to y prime. Okay. And one thing that's also worth noting is if y is, so by the first remark, right, it makes sense to refer to the least upper bound of a set if it exists. Not just a least upper bound, the least upper bound, right? And actually, maybe I should have state this remark before the notation sup s, because if you say sup s for the least upper bound, then there's an assumption that there's only one supremum. But now we know that there really is only one supremum if it exists. And if y is the supremum, or least upper bound, same thing, of s, so suppose that y is the least upper bound of s, and x is a real number that's less than y, then there must exist some element of s, say little s, with the property that x is less than s. Okay, let's see why that's true. So let's say this is your real number line, and let's say s was something like this, right? Now, if y is the least upper bound, so in this case, it's here. If you have a real number x that's less than y, okay, so maybe x is here, then there must be some element of s that's greater than x, and that's because if there wasn't, right, this is one of those things where you just kind of have to think about what, you kind of just have to think about it until it makes sense. But the reason is, if there weren't, then that would mean that x is greater than or equal to s for every s in s. But that would mean that x is an upper bound. So x is an upper bound of s, but if y is the least upper bound, then x can't be less than y, because then x would be an upper bound that's lower than the least upper bound. But then x would be less than the least upper bound, namely y. So that's the reason. So that's just a useful thing to keep in mind. It might come up in some proofs later. Okay, so we have another definition, the maximum of a set S. So if a subset S of R has a greatest element, so a greatest element is an element of S, so in other words, i.e. an element of S, say x in S, such that x is greater than or equal to S for all little elements, for all little s in S. Okay. Then this element is called the maximum of S, and it's denoted max S. Alright, and if S has a least element, naturally we call that the minimum of S, and denoted min S. Okay. Well, behind that statement is, again, the assertion that you can't have two least elements or two greatest elements, and the proof is the same as what we did before. Now, if um, if S has a maximum and S might not have a maximum, if X has a maximum, then the max of S is just the supremum of S, right? Because the maximum, if S has a maximum, then the maximum is greater than or equal to all the elements of S. So in other words, it's an upper bound. Now, why is it the least upper bound? Well, suppose, let's see. Oh, well, this is another one where you kind of just have to think about it. I mean, suppose that there were, so least upper bound means that it needs to be less than or equal to any other upper bound. So suppose that you had an upper bound, say A, for the set S. So, okay, so let's just write it a little bit. So the reason is, we know that max S is an upper bound. Okay, why is it a least upper bound? If A is another upper bound, well, we know that A is greater than or equal to S for all elements of S. In particular, so A is greater than or equal to the maximum of S, right? Because the maximum of S is an element of S. But the inequality A is greater than or equal to the maximum of S tells you precisely that that the maximum of S is less than any upper bound of S, which means that max S is the least upper bound. So that's the reason. Okay. So remember, what am I doing to prove that something is the supremum? I'm checking that these two hold, right? First, you have to check that it is an upper bound to begin with, and then you say let A be any upper bound. Then you have to prove that the thing that you're trying to say is the least upper bound is less than or equal to A, which is what we explained here. Right. All right. So let's look at some examples. So every finite set S of real numbers, right, has a greatest element. Okay, I think that's clear. But if you have something like the open interval from 0 to 1, S does not have a greatest element. Because the supremum of S is 1, which is not an element of S. Right. Right. Yeah. I mean, if there were some element in the interval that were greatest, the thing is that whenever you have an element in this interval, you can always, so here's the interval from 0 to 1. Whenever you have an element in this interval, let's say this is x, you can always take a number that's halfway between x and 1, right? And then you can always take a number that's halfway between that. So you can always take elements that are greater than the one before it that are still elements of S. And so that explains why S does not have a greatest element. Okay, so that's one argument. And then the other argument is just that the supremum is 1. And if S did have a greatest element, it would be the supremum, but the supremum is 1, and that is not an element of S. So there's something to mention, which is I'm using the phrase S does not have a greatest element. What that means is that there's no, so a greatest element, when we say that a set has a greatest element, we mean an element of S, right? When we say that S has a supremum, so this set has a supremum, which is 1, that element, we don't mean that that element is an element of S. Okay, so that's an important distinction to make. Another example would be, let's say that S is the set of negative numbers. Does that have a supremum? Well, yes. So here's 0, here's S, right? All the negative numbers. The supremum of S is 0, but S does not have a greatest element. Does not have the greatest element. In other words, there's no maximum of S. Alright, now we're ready to state the last axiom for the real number system. So, assuming that you've learned about the different axioms of the real numbers, the most important one is the least upper bound property. So the least upper bound property says a non-empty set of real numbers that is bounded from above has a least upper bound. Okay. Sometimes this is called the completeness axiom. So what's the meaning of this statement? That whenever you have a non-empty set of real numbers that's bounded from above, it has the least upper bound. Well, the idea is, so the intuition is, that there are no holes in the real number line. Of course, that's not super precise, but the idea is, here's the number line. So suppose that suppose that the real number line was like a line, except it's like missing some number. So let's say that this element is not a real number. So let's say that there's like a hole here, right? Well, if there was a hole there, then if you look at the numbers to the left of the line, this set S would be a non-empty set of real numbers that's bounded from above that does not have a least upper bound. Right? If this green number was somehow not there, then there would be no least upper bound. So the fact that you have to include a least upper bound in your real numbers basically is what makes the real numbers in some sense complete. Like it's somehow not missing any numbers. Right? So this would be the supremum of S. So if that were gone, if there were a hole, then the set S would not have a supremum. Okay, so we've talked about upper bounds. Let's talk about lower bounds. It's exactly analogous, so I'm just going to explain this very quickly. So a real number is a lower bound for the set S if for all little s in S, A is less than or equal to S. Okay, so that's the first definition, and A is a greatest lower bound if A is a lower bound of S, and if there exists no larger one. So it's the same, it's just pretty much the same as before. So let's say this is your set S. Then all the numbers here are lower bounds. Right? These are all lower bounds, S including 0. Including 0. And the greatest lower bound would be 0. Right? That would be 0 would be the greatest lower bound of S, also written as inf S, the infimum of S. And we say that S is bounded from below if it has a lower bound. So completely analogous to upper bounds. Now let's prove a statement. So the completeness axiom, or the least upper bound property, says, let's put a star to indicate that's important, is that a non-empty set of real numbers that's bounded from above has the least upper bound. So we can ask, is it true that if it's bounded from below, that it has the greatest lower bound? And the statement is yes. Yes. So every set S of real numbers that is non-empty and bounded from below has a greatest lower bound. Alright, let's prove that. So let's just draw a picture just to get an idea of what's going on. So you have some set S that's bounded from below, but possibly not from above. So let's just do one. Let's say this is S, and then it includes all these points here. They go out forever, right? Just going out forever. So let's say that's our set S. So this is an example of a set that's bounded from below, but not bounded from above, right? Okay. Well, intuitively, we see where the greatest lower bound would be. It would be this element here, right? And the idea is we want to use the axiom above that says that if you have something that's bounded from above, it has the least upper bound. So the idea of this proof is to connect the greatest lower bound with the least upper bound. And what we're going to do is we're just going to multiply all the elements of S by -1. So that's just going to flip all the elements of S across. And what's going to happen is we're going to get something that's bounded from above, and then we can apply the axiom. So let's write that down. So consider the set S prime, which is all real numbers such that negative x is an element of S. In other words, these are just the numbers obtained by multiplying x and S by -1, right? So if negative, let's make it clear. If negative x is in S, then x is in negative S, right? In other words, negative s being the numbers you get by multiplying by negative 1. So that's s prime. All right, so the first assertion we're going to make is that s prime is bounded from above. Let's prove that. So if A is any lower bound of S, which we know exists because S is bounded from below, then, okay, A is less than or equal to S for every S in S. So now if you multiply by negative 1 on both sides, we get negative A is greater than or equal to negative S for all S and S. And the elements of S prime are just of the form negative S. So negative A is greater than or equal to X for every element X in S prime, which proves that negative A is an upper bound of S prime. So that shows that S prime is bounded from above. And now we can apply the least upper bound property. That says that S prime has a least upper bound, has a supremum. Let's call that supremum y. And now we claim naturally that negative y is an infimum of S. We don't want to say that negative y is the infimum of S because that assumes that there is an infimum in the first place, right? Of course, once we know that there is an infimum, then we know that there's only one, so we can call it the infimum. So we're trying to show that negative y is an infimum of S, and the proof of that is, well, we know that this is, do we know that negative y is less than or equal to every element of S? Well, okay, that's kind of easy to see, but basically I'll write it down anyway. So first of all, let's show that negative y is the lower bound. So if, sorry, an infimum of S. So if A is an element of S, then negative A is an element of S prime, so y is greater than or equal to negative A, and then that implies that y prime, which is negative, oh, I didn't use the notation, I just called it negative y. Negative y is less than or equal to A. So negative y is a lower bound of S. So we're halfway done, because that's the first thing we need to show to prove that something is an infimum. And then the next thing we need to prove is, so suppose that Z is a lower bound of S. What do we need to prove? We need to prove that Z is less than or equal to negative y to show that negative y is the greatest lower bound. Well, we have, if Z is a lower bound of S, then we know that negative Z is an upper bound of S prime. since y is the supremum of s prime, we know that y is less than or equal to negative z, and that implies that negative y is greater than or equal to z. And that proves that. So that's the proof of the theorem. Okay? So the least upper bound property is very important. Oh, maybe I should just mention that if you look at the different axioms of the real numbers, right, if you just leave out the completeness axiom, then, so let's just write this down. So why is the completeness axiom important? Well, if you leave out the completeness axiom and just write down the other axioms of the real numbers, the rational numbers satisfy all those other axioms. So this axiom, the answer is, this axiom distinguishes the real numbers from other kind of number systems. For example, if you take just rational numbers, so first of all, let's assume that we know that the square root of 2 is irrational. There's a standard proof of that. Then you can take the set, you can take a sequence converging to the square root of 2. So you can take 1, 1.4, 1.41, etc. This set of numbers that gets closer and closer to the square root of 2. So what would that look like? So let's say this is S. So here's 1, 1.4, 1.41, etc. And you take this set of numbers, and here's the square root of 2, which is not a rational number. Well, this set is a set of rational numbers but wouldn't have a supremum. That does not have that is rational. Right? So if you can just imagine somehow not including irrational numbers, let's say there was no such thing as irrational numbers and they were just rational numbers, then you can have a set S that does not have a supremum. Right? So by throwing in the irrational numbers, we have a set, we have a number system where every set has a supremum. So that's why this completeness axiom distinguishes R from the rational number system. See, the rational number system does not have this completeness axiom property that every set of rational numbers has a supremum. Right? It's only when you look at all real numbers together that you can make a statement like that. And of course, these are axioms of the real number system. So, you know, it still requires proof that there is a number system that satisfies all of them, and that's something that is sometimes proven or sometimes not proven, the construction of the real numbers from the rational numbers. But anyway, the point is that the real numbers satisfy the completeness axiom, the least upper bound property, but if you imagine just a set of rational numbers and just pretend that there's no such thing as irrational numbers, that would not have the least upper bound property. Okay, thanks.